All right, in this video, we're going to look at the critical angle and total internal reflection. So both of these come off of Snell's law, right? And so let's real quick review of Snell's law, right? Here's my fancy laser thing, and I got a glass block down here. And this beam is going from air to glass. This isn't really glass, it's some sort of plastic, I don't know. We'll call air in 1 and glass in 2. And remember, when you're doing optics, draw your normal line first, right? So there's my normal line when it comes in. And because this beam comes in directly in line with the normal, there's no angle, right? So if there's no angle between the normal and the beam of light, then there's going to be no refraction. And so you can see that down here, this beam comes out straight, just like it went in. There's no bending, right? Okay, that's boring. So we know from Snell's law that if I bend this and I make this shine in at an angle, right, there's an angle of incidence here, and you can see the angle of refraction in the glass. I can't draw it in the glass, but I can draw it down here when it comes out, because again, it's coming out the bottom here perpendicular, so that's the same direction it's traveling inside the glass. And so here is my angle of incidence, I'll call that theta 1, and here's my angle of refraction, I'll call that theta 2, if I can write correctly, right? So when N2 is greater than N1, nothing special happens. And so I'll show you what I mean by this. When N2 is greater than N1, nothing special happens. Okay, so watch. If I make this angle bigger, theta 1, I'm going to make it larger, right? See how I'm making the angle of incidence larger. The angle of refraction got larger too, but it didn't get as large as this one, right? So what I mean is this angle is changing more than this angle. So eventually there's going to come a point, let me see if I can get as close to 90 degrees as I can, right? Because eventually this thing only has 90 degrees to work with, right? Because eventually it's going to go parallel to the surface and nothing happens. So I'm going to do it like, see if I can do it right here. That's as close as I can get. So look at that. That's, I mean, it's not 90 degrees, but it's, I'd say like maybe 75 degrees. That's really big. And if you look down here, here's the beam coming out. That's not even, I mean, it's barely 45 degrees. So what I mean when nothing special happens, I mean that you're going to run out of room over here before anything over here can happen, right? When you're going from something with the low index to something with the high index. The special case is when you do this the other way. So let me flip this around. Now, in this case, I have N1 is greater than N2. And when N1 is greater than N2, I have a chance of getting total internal reflection. And let me show you what that looks like. Right, so this is when N1 is greater than N2. Okay, so watch what I mean. I'm going to make my angle bigger. So here's my normal, right? Whoops. Here's my normal. Here it is coming out. I'm going to make this angle a little bit bigger. Oh, look at that. There's immediately a big difference, right? You can see the difference here. This angle here got big. This one changed more than that one, as opposed to the other way. Remember before, this one didn't change as much, right? So watch what's happening. I make this angle bigger and bigger and bigger and bigger, right? And eventually you can see there's going to come a point where this beam is going to hit 90 degrees, right? So, I mean, what do you expect would happen when this refracted beam approaches 90 degrees? What do you think is going to happen? Well, let's find out. So here we go. Did you see that? As soon as it crossed over to 90 degrees, watch, this is as close as I can get it right here. You can see the beam right there. As soon as it hits 90 degrees, boom, it's reflected out. Look at that. And it's just like a mirror. You can see the angle coming in is the same as angle coming out. And there's no light coming out down here. It's not like, oh, some of it's refracted, some of it's reflected. This is total internal reflection. It's acting as if this surface back here is a mirror, right? So when you hit this point right there, right? See how I still got some light coming out this way, but as soon as I hit that angle right there where it's 90 degrees and that happens, this angle right there is called the critical angle, theta C. Critical angle. At the critical angle, you get total internal reflection. Okay, so let's look at the math behind this. When I have something going from a high index of refraction to a low index of refraction, when N1 is greater than N2, you have a chance of getting total internal reflection, right? So let's look at this. It all starts with Snell's law. Snell's law is pretty easy to use. N1 sine theta 1 equals N2 sine theta 2. So let's look at what we know. I know when this hits the critical angle, this is going to be going this way, right? It's going to hit 90 degrees and it's going to reflect, right? So I know that at the critical angle, theta 2 is equal to 90 degrees, okay? All right, so I also know that if I take the sine of that, the sine of 90 degrees is equal to 1, right? From our trig functions, you should know that. So if I take this and I substitute it in here, let me rewrite this. N1 sine theta 1 equals N2 times 1, right? So what I'm doing is I'm putting 90 degrees in for theta 2, and I'm calling theta 1 the critical angle. So when the critical angle is here, this is 90 degrees, right? So let me change this. I'll make that theta c. Okay, so now I want to solve for critical angle. How can I get a formula that tells me critical angle? So let's do some algebra. I can divide over N1, right? So equals N2 over N1. And then I can take the arc sine of both sides. That'll cancel out the sine here. So my critical angle is going to be equal to the arc sine of N2 over N1, right? So there is a formula. And remember, this is only when N1 is greater than N2. That's the caveat, right? This only occurs when N1 is greater than N2. So look, the critical angle is dependent on the indices of refraction of the two things, right? So you don't have to actually do that. I mean, you can do it in the lab and test it out and see what the critical angle is, but you could just know the indices of refraction and solve for the critical angle. And on vice versa, you could take something like this and you could measure the angle and see when it reflects, and you could use that to figure out what the index of refraction of this material is, right? So total internal reflection is really cool. If you take something like this, right? If I take a piece of glass and you look at it, if I shine this in at the right angle, you can see how inside the piece of glass it reflects off that surface. See how it goes here and it bounces down here and then it comes up here? And these surfaces are acting like mirrors, right? So what would really be cool is imagine if you could take like this piece of glass and extend it out that long, right? So take a piece of glass real long like this and I could shine a beam in here. What would happen is it would bounce off back and forth and back and forth and back and forth, and it would lose no light at those interfaces right there, right? You get total internal reflection. So this beam could go all the way, travel down this piece of glass. And wow, that's what a fiber optic cable is. That's how these things work, right? Fiber optic cables is basically just a real long, thin piece of glass that light reflects off the inside. Fiber optics are really cool. Another thing, you can use glass and prisms and stuff like that as a mirror, right? So watch this. If I take this prism and I put it here at an angle below the critical angle, see how it refracts out? But when I hit the critical angle, it reflects straight back out. You can see that beam comes in, reflects off this surface, and bounces back out. This principle is used in something called a retroreflector. You can make a retroreflector that acts like a mirror, but it's better out of a piece of glass. So one place you can really see total internal reflection is underwater, like in a pool. From the bottom, if you look up, you can see things above the surface directly above you. But if you look out far enough to the side, you'll pass the critical angle, and the surface of the water outside that is going to look like a mirror. This is something divers see a lot. It's called Snell's window because it kind of looks like a window to the world above the water. Okay, so real quick review. Only formula you need. Critical angle is the arc sine of N2 over N1, right? Just remember to be in degrees in your calculator. And the key, this only works when you're going from something with a high index of refraction to a low index of refraction. Something like water to air or glass to air, something like that. It doesn't work when you go the other way around.